Okay, so this morning Mikkel gave a presentation on how EEG as a research field works. Very much into how we can use this for cognitive research, for clinical research, how the EEG that we're recording the outside relates to the neurophysiology on the inside, like at the different spatial scales. Tomorrow we're gonna go more into the technical details of how EEG works, how we can design experiments, but also how we can record them. But of course, something that also needs to be discussed is how you organize your EEG research. And in that organization, things are quite different between developed countries, like rich countries such as the Netherlands, and Africa. And that is something that I want to highlight in this presentation. So I want to go over the difference that I'm aware of. But I'm also curious to hear your feedback or your ideas on like challenges that you would encounter. So rather than taking the perspective from the lab, from the participants, we're just going to zoom out. We're going to forget the EEG system, all those type of details. We're going to look more at like the organizational structure. And what I'm going to do is, because like every institute is different, I'm just going to give you the perspective from the institute where I'm working. So I'm going to explain you how we work. And based on that, we can start a discussion on how you might be able to work. So I'm going to talk about the organization of the research infrastructure, financial and organizational constraints that imposes. And I'm going to provide some real numbers, like what does it cost us and what might it cost you in order to run EEG. So I've tried to come up with realistic numbers. Then I'll go into like how can you organize your lab to make it run efficiently. Like not only that you can run it, but also that you can run it efficiently. And then after that, I want to go into some practical challenges, such as the difference between European hair and African hair, and some ethical and legal differences. So this is very much going to be a comparative presentation. I'm going to present what I know about the European situation. I'm going to present what I think applies to the African situation, but I'm not 100% sure. And then if you have inputs, that is something that we can discuss. So this is the building of the Donders Centre for Cognitive Neuroimaging. It's based in the Netherlands. So we're now here. This is where Nijmegen is. By the way, this is where Denmark is. So Mikkel is from here. I'm from here. And the Donders Centre for Cognitive Neuroimaging, the DCCN, is part of the Donders Institute for Brain Cognition and Behavior. The Donders Institute spans multiple centers over the whole university, and the Donders Institute is part of Radboud University in Nijmegen. And this is confusing, and it's not only confusing for you, it's also confusing for us. Like it's always unclear in which part of the Donders you're working. But what I can tell is about the Donders Centre for Cognitive Neuroimaging, because that's really its own entity with its own financial budget, etc. At the Donders Institute at Radboud University, we also have the Donders Centre for Cognition, the Donders Centre for Medical Neuroscience, and the Donders Centre for Neuroscience, which are aligned with the science faculty, the medical faculty, and the social science faculty. The Donders Centre for Cognitive Neuroimaging has 2 EEG labs. We have an MEG scanner, and we have 3 MR scanners. Those MR scanners are only for research. We also have a hospital on the same campus. The hospital has its own scanners. So our scanners are typically slightly better than the ones that they use in the hospital, because we're using research scanners, so we're always using the latest technology. So at this moment we have 3 Tesla scanners, but 2 years ago we got a large grant, and at this moment we're building a 14 Tesla scanner. It's going to be the first 14 Tesla scanner in the world if we succeed. But that's going to be a really exciting thing with which we can get extremely high resolution imaging. We also have labs for brain stimulation, so we can do TMS, transcranial current stimulation, TACS, TDCS, and we can do focused ultrasound stimulation. And then we have multiple behavioral labs. In our building, so in our center, we have about 250 researchers that are using these labs. We have a technical lab support group mainly engineers, that work together with an EEG lab manager and an MR lab manager. So the MR lab manager is that's Paul. He's always downstairs in MR lab. He basically has his desk there. He's supervising the MR research. If people have MR questions, they go to him. If people like me who don't know which buttons to press to do an MR scan, I would just ask Paul. Paul would make the MR scan for me. But in principle, the researchers do their own scans. Paul is just there to train researchers and to provide supervision. The same goes for the EEG MEG lab manager. So Miranda is our EEG MEG lab manager, and she provides training to researchers that start in the center. So basically, we have a sort of a driver's license that people have to get. So first, people have to look along with an existing experiment to see how all the equipment works. Then they do an experiment under supervision of Miranda. Then they do an experiment by themselves, where Miranda looks over their shoulder to check whether they're doing everything correctly. And if they're then doing everything correctly, they become certified lab users. So we have the certification process both for the MRI and for the EEG and MEG. So that's more or less how it works. So over the whole campus of Radboud University, there's about 10 EEG labs. To be honest, I'm not even sure. But we have multiple EEG labs because multiple departments have their own EEG lab. Some of them are used by a few people, which also indicates that EEG does not have to be done at a large center such as the DCCN. Like the DCCN, because we have these very expensive scanners, we have this large support group, and we're really operating by having many people use our facilities. Whereas at some other departments, they basically said, oh, let's just get an EEG amplifier, let's just convert an office into an EEG lab, and they're just using it with a few people. So that is also a possibility. To give you some idea on the organizational and financial consequences of this at the Donders Centre for Cognitive Neuroimaging, so my center. So all the facilities, all the research facilities that we have at our center, including the EEG labs, are available to all the researchers on the campus. The university pays a lump sum for maintaining the building, for maintaining the infrastructure. But then the professors apply for grants. Based on these grants, they hire usually PhD students, or like master students can join, but master students are not being paid. But in such a grant application, you would also apply for lab usage. And the researchers typically the PhD students that do the hands-on research, that use the labs, they then pay for the labs from the grant. And for the EEG labs, the tariff that we have is about 30 euros per hour. So that means if you're going to scan 30 participants, it's about 1,000 euros, if an experiment is like 1 hour. So that's just like the order of magnitude that we're talking about. So we have this infrastructure, and I'm going to show you the labs a little bit later. I made videos of the labs, so I can show you what type of equipment we have. So in principle, the researchers can use the equipment that is available, but of course sometimes we need new equipment. If the equipment is not too expensive, the center buys it. But if the equipment is expensive, then the professors have to apply for grants to buy new equipment. So that's more or less how it works. And also, if something breaks and it's being used by a lot of researchers, then we would pay it from the center budget. But if something is only used by a single researcher or by one group, then it's that group that has to pay for it. So part of the budget that we have for the infrastructure comes from the university that pays us like a fixed amount per year. And part of it is flexible, and that comes from the grants that are being applied for by professors, by people like me, and all the other principal investigators. And it's mainly the Dutch government. So we have the NWO, the Netherlands Foundation for Dutch Scientific Research, and the European Union. Those are the primary sources where we get funding. Also, just wanted to show you, so EEG is not expensive. You might say 30 euros is quite a bit. So this is from our intranet. this is the price that we pay for all the different research facilities. So 1 hour on the MRI scanner costs 233 euros at this moment. And this tariff basically fluctuates over the years, depending on how much usage there is. If a scanner is used a lot, it gets cheaper, because the scanner has a fixed amount that we have to pay for it to maintain it. So then we can spread the cost over more people. The MEG lab is at this moment the most expensive. It costs 500 euros per hour. That is a significant hurdle also for Dutch researchers. But still, the grants typically allow us to put in enough money to scan like 30, 40, sometimes 50 participants. So in a typical grant for a PhD student, we would have order of magnitude of, like, let's say 50,000 euros for scanning costs. Because if you do MEG, we always get the MEG, but we also get an MRI of our participants. EEG and TMS, they're cheap. Like the equipment is not really that expensive. It's maintenance is not expensive. The MEG and the MRI scanners, they require a lot of maintenance, so that makes them expensive. The EEG system is just sitting there. It doesn't require maintenance. Only when it breaks down, we replace components. So EEG and MEG are cheap. And then we have a new MEG system, which at this moment is still being sponsored. So that's the OPM system, which is not too expensive. And then we have functional ultrasound. Behavioral cubicles can be used for free. So we have a whole bunch of labs that you actually don't have to pay for. And that's also on purpose, because we would rather have people use one of the less expensive labs without the fancy equipment for piloting before they start moving into the scanner. Scanner is often busy, so we would rather not have too many pilot experiments in the scanner if those pilot experiments relate to behavior. So this is also a choice. Yeah, and what I did not mention, we have a collaboration with a city in Germany, close over the border, where we have access to a 7 Tesla scanner, but that always requires some negotiation. Okay, so the cost of setting up an EEG lab, like if you start from scratch, if you don't have anything yet, I would say like the cheapest EEG system that you can use, the cheapest EEG system that I've brought, it costs about 1,000 euros. A research grade system, so the most fancy EEG system that I brought, costs around 30,000 euros. And then in between, there's a lot of choices. You can make it more expensive than this, then you get nicer equipment. If you make it cheaper than this, you get crap equipment. And I wouldn't simply not waste my time on using equipment with which you cannot do good research. But from about 1,000 euros onwards, you're in business, I would say. That doesn't mean that you can do everything. And that's what we're going to see tomorrow morning. If we're going to try out the different systems, you will see that they're very different in what they can do. And I'm going to highlight the difference between the systems. So I have a whole stack of computers with me. I've borrowed computers from ABDN. Typically for an EEG lab, you need at least 2 computers. So you need one computer for data acquisition, so that's connected to the EEG amplifier. You need one computer that is for stimulus presentation. Actually, in most of the labs, we have more computers, but I would say 2 computers is the minimum. So that means that the minimum for setting up a lab, I would say, is like 2,000 euros, more or less. By the way, I hope you're all familiar with euros, right? Like that you have, because I could also, like, euros and dollars are not that different. So if I'm saying 2,000 euros, it's a little bit similar, like dollars are with, it's like that would be like $2,500 US dollars at this moment. So then another cost that you have for running an EEG lab is supplies, or consumables, as we sometimes call them. So things that you use once and then throw away. So that is electrogel, tape, all sorts of small stuff, syringes, and that really depends on how much you measure, because it just scales because you throw it away. It's not very expensive. It's like a few euros per measurement. But still, it is something that you have to keep in mind. And also something that you have to keep in mind is if you don't use the lab very often, it might be that certain things get overdate, and then you have to throw them away and then you have to buy them new. because of the hygiene. So I also brought some bottles of gel, etc. And we're going to use that, but I would say like a bottle of gel would typically be 10 euros. And then you can record, like easily you can record 50 people with that. And then slightly more significant compared to the consumables are the maintenance costs. So I already mentioned MRI is expensive because the maintenance of the MRI system is expensive. MEG is expensive because the maintenance is expensive and because it works with liquid helium, which is very expensive. EEG by itself, if it sits on the shelf, doesn't break. But if you start using it, then you might be pulling cables, so stuff breaks. And it's often cables or connectors or those type of things that break. So we're doing quite some EEG experiments and already for 20 years. So we have quite some experience with that. So I would say that you should assume that every component that you have in the EEG lab needs to be replaced about every 5 to 10 years. So including the amplifier. At a certain point, the amplifier is not going to work anymore. One of the challenges that, for example, that we have with the amplifiers, with the software which Mikkel and I have been working on over the last weekend, is we have to install it on the computer that we now have. And then we have like a Windows 10 computer and a Windows 11 computer. And then the software doesn't work on one or the software doesn't work on the other. So that's also why you depend on the support from the companies. Because if you have an old computer, well then perhaps you cannot use the new software. But also if you buy a new computer, well perhaps the old software does not work anymore. And if the software doesn't work, the amplifier doesn't work. So that's just something to keep in mind. And for that I would basically budget, let's say 10 to 20% of the cost of the equipment per year. So that means that if you have a 30,000 euro amplifier or 30,000 euro EEG setup, I would budget approximately 3,000 euros a year just to keep it up and running. And that's assuming that you use it regularly. One of the things that we find that breaks relatively often or that wears down are, for example, the caps and the electrodes. And that's just due to usage. So that's something that you then have to keep in mind. Something for which I cannot provide a number is that ideally you would want to have everything set up in a permanent room in the lab. So we've taken everything with us. And it's a little bit scary to take all the expensive stuff on the airplane and to carry it around. Usually we would just keep everything in the lab with computer setup, with all the cables such that you cannot trip, that you cannot break anything. So having a dedicated lab is definitely beneficial. But of course it depends a lot on what the university is charging for the space. Like for us, the university is actually, so the university is giving us money and then we have to pay the money back to the university for the space that we have. So that's how it works. If you have an EEG lab, you can make it really fancy by installing a Faraday cage. A Faraday cage is like a metal shielding that you put on the walls. And then you can still put nice covering over it so that you don't see the metal. And the metal shielding over the walls, like if you do that on all the 6 walls of the room, it keeps the environmental noise out. So you can get more noise-free recordings in a Faraday cage. But of course, installing a Faraday cage makes the lab considerably more expensive. Because it's not only the walls that need to be done, but you have to think how do you do the ventilation in the room then, because the standard doesn't work anymore because you have to cut holes in the metal. You have to think about the door that has to open and shut. I will show this in the video as well. So we have Faraday cages, and that does make the labs more expensive, but you only have to install them once. So we installed them 20 years ago when our center started. We have not replaced them since, and they're still useful. So given these numbers, I would say that an initial investment range from 2,500 for a minimal, like a really minimal system, up to 50,000 or above for a fancy system in a nice room. And then the yearly operating cost, they might range from 250 euros up to 5,000 euros. Just to give you an idea on how expensive it is to set up an EEG lab. The way that we operate in our center is really as a center. So our EEG labs, but also our scanners, are used by many people. And that makes it possible for us to have so many scanners. If you would have a single scanner for a single professor, that would not work, because none of the professors is scanning enough to warrant their own scanner. So by sharing, we can make it more efficient. So having many users means that investments and operational costs are distributed, which of course means that you can get the cost down, or in our case, we can get more equipment. So that's how we work. Having more users also means that the EEG lab is more used and that more expertise is built up. However, this doesn't require that you also work together and share expertise. So I think one of the very important strategies that we use in our center is that we have lab-specific meetings. So not lab as in a PI group, but lab as in a technique. So we have an EEG meeting in which all the EEG researchers are invited. We have that every week. We have a meeting with the EEG researchers, and then we just discuss EEG stuff. So new students come in, they explain their problems. The older students can help them, and I'm typically there, I can help as well. And we basically make a plan, and that helps to build a community. And this community then also meets in the labs. So people know that the equipment is being used by others, and it helps building this sense that we can do this together and that we benefit from each other. Which is very different from the structure that I've seen at some other centers, where people claim the equipment, where no one else is allowed to use the equipment. And for us, the culture is very much about sharing. EEG research is, by its very nature, it's very interdisciplinary. So having multiple disciplines working together contributes to the quality and efficiency. So I'm a physicist by myself, but I work together with people with a medical background, with a psychology background, with neuroscience backgrounds, many different disciplines, and we don't really ask from each other, what have you done in the past? But we just benefit from each other's expertise. So that's also how I'm benefiting from Mikkel's expertise as a psychologist. So together we complement each other. And I would say that's also very important if you think about setting up an EEG research facility, is that you should think about working together with people that have a different interest than your interest. Tomorrow we're going to talk about synchronization. I brought an Arduino, which is like one of these small microcontroller boards. This is typically one of the things that you need in an EEG lab. But as a psychologist, or as a neuroscientist, you probably don't know how to program them. But for an electrical engineer, that's not that difficult. So that's why the collaboration between different departments can really help to improve the research quality and creates interesting research opportunity for multiple disciplines. There's also a negative point in having multiple users, and that is that it means that it's hard to ensure that equipment is properly handled. The more users we have, the more policing is necessary to make sure that the users don't misbehave, because the users feel less responsible. And untrained users are more likely to break things. So this is something that we see over the years. Sometimes we have a generation of students that somehow does not feel so responsible for the lab. They're just using the lab, and in a way they're abusing the lab, and then stuff breaks, and then we have the headaches and we have to replace it. So if you have a lot of users, you also have to be aware that you need more coordination between the users, and you need to have more support, because then you want to make sure that the users don't interfere with each other's research. And I will show you in the videos how we've implemented this. So we've tried to make all our labs very similar, but that is also, of course also because we have the technical support group to help us with this. Oh yeah, see video. So I wanted to show you two videos. So what I did is I took, just before flying here, I took two short videos of two different labs. So one lab at the DCCN, so the Center for Cognitive Neuroimaging, that's my building. And then one video of the lab at the Center for Cognition, which is in another building. And I'm collaborating with both, so I know quite a bit about both. But they're different labs, and after the videos or during the videos, I can just stop the videos, and I can explain also what you see and why the labs are different, like which different choices were made. And I apologize because it's really stupid. I just took it with my phone upright, so it's not the most efficient way of using the screen. Let me just, I'm gonna hide these, move this to the middle. So this is the EEG lab at the DCCN. It's actually going quite fast. So what you see here is the different computers that we have. So we have an acquisition computer and a stimulus presentation computer. That's the core. The computers are over here. But then we also have two more computers. We have one computer for the eye tracker, and we have one computer for general purpose stuff. Because like if you're running an experiment, and so the eye tracker is busy, the EEG is busy, the acquisition computer is busy, and then you want to take notes. So that's why we have the fourth computer. In this corner, oops, I think I'm going to zoom in. So there's a bed, sometimes we do sleep EEG research. In this corner, you see the EEG equipment. So in our labs at the DCCN, we're using amplifiers from Brain Products. Brain Products is a German company. And each of these, so this is a battery pack, this is an amplifier. This is a battery pack, and these are two amplifiers. So each amplifier is 32 channels. And most of the time, we do recordings with 64 channels. Sometimes we do recordings with 128 channels. So what we can do is we can combine this one and this one so that we can have 128 channel recordings. This gives us flexibility because we then can actually use the amplifiers in different configuration. We don't always have to do 128 channel recordings. And if we're, for example, doing recordings with children who have a smaller head, we typically would only do 32 channels. So these two are like separate amplifiers. Actually, so these are amplifiers that we use specifically for recording auxiliary channels. So this morning there was a question, can you also record EMG and EOG and those type of things? Can you record that together with the EEG? So these amplifiers, they don't have input for bipolar channels. So that's why we're using these boxes, and this is a bipolar input. The system is modular. So that's convenient, we can expand it, but the system is also expensive. So one of these amplifiers, I think, is in the order of 20,000 euros. So this is a relatively expensive company, I would say. But yeah, in the Netherlands, we always talk about the German Gründlichkeit. So the Germans are very thorough in the quality of the products that they made. And so we've been using their equipment for 20 years, and it just works. And for us, that's worth quite a thing. So we're not too ambitious, like exploring new things if this just works, and then we just pay a little bit extra for something that just works. So this is robust equipment, but it's also expensive. What you also see here is an iPad, which we're using to record electrode positions. That is something I can show later in the week, as I didn't bring the iPad with me, but for some studies, we want to know exactly where the electrodes are on the scalp. And then we use the iPad with a 3D scanner. So there's a lot of things that are being charged because a lot of the stuff works on batteries. So that's the iPad. That's all the things that need to be charged. And that's, again, the computer setup. So this is our strategy of trying to make it robust in the labs. So each of our labs, so each of the MRI labs, each of the MEG lab, or also each of the EEG labs, has a 19-inch rack. So this is like a computer rack. And what we tell our users of the lab, so our PhD students, is that they can touch the front, but not the back. So the idea is that all the cables are out of the way. The researcher should not be messing around with cables, because if one researcher starts swapping out cables, the next research comes later in the afternoon and then it doesn't work anymore. Each of the racks has a schematic on the side so that you can look up which buttons to press, because the labs have, as you will see, they have different computer screens. And for example, with this box, we can switch where a certain screen is being shown. So we can switch between the computer being shown on inside the lab or outside the lab. And there's like audio equipment as well. We do a lot of language research. There's like a participant monitoring system so that we can see what the participant is doing. And this is basically the same, it's a very similar setup that we have in all the labs. So participant monitoring, audio, the 4 computers. Oh yeah, and so what I should quickly point out. So over here, so the blue box, that's a box that we use for synchronization. I'm going to talk more about that tomorrow, but keeping all the responses, keeping all the stimuli and the responses in sync with the EEG data, that is quite challenging. So for that, we've developed over the course of the years our own solution, and I brought one of them, and I'm gonna show it to you. I brought a small version of it, but that's what we call the BITSI, and every lab basically has a similar solution like this. Like a lot of labs invent their own, but it's relevant in every lab. So this is the table on which we typically put the amplifiers to roll them around, and this is the area where we wash up. So we have the caps hanging there to dry. These are the electrodes. We're using active electrodes. So these I'll talk more about that tomorrow, but they have a small preamplifier. Sometimes for some studies we also use passive electrodes, like the more clinical use. And these are 228 Allen caps that happen to be hanging there that we use for sleep studies. They're very flat. And then we have caps in different sizes, but also slightly different layouts. So this is the 1010 layout, the other one were the equidistant. Again, I will tell a little bit more about that tomorrow. And then let's go into the lab. So I'm now switching on the light. And what you can see is that there's 2 doors with a thick metal wall in between. So this is all metal, and that's this Faraday cage. So there's metal all around in the room to block environmental fields. An advantage is as well, I'm just going to quickly stop it. We're at the Center for Cognitive Neuroimaging, we're doing a lot of language research. The lab being like in a separate booth also has the advantage that the booth is sound attenuated. So the lab where the participant sits is both very silent and it has this electrical shielding with the Faraday cage. The lab is also placed such that it's not directly against the corridor. So if there's people walking in the corridor that are talking, it does not disturb the participant. And for us that is very important because we have a lot of these tasks where the participants have to pay close attention, and then we don't want the participants being distracted, or for example to be the distraction based on the time of the day, because at certain moments of the day there's going to be more traffic in the corridor than other moments. So that's why the labs, the booths are away from the corridor and sound attenuated. So that was the fiber optic cable, and here you see so usually would have a slightly better chair here. So this is where the participant is sitting. This is the eye tracker, which then folds up, and that's the screen, and these are the button boxes. I'll also explain tomorrow why we're using the button boxes. We're not using the computer keyboards too much. And then we have cameras, we have speakers, and that's more or less the EEG lab. Any questions about this? Oh, sorry.
The photon stimulator.
So we're not doing clinical research. So we don't have a photonic stimulator. There's no epilepsy patients in here. We do sometimes do research on clinical population. So for example, we had one project in which we had stroke patients. So in that case, we do invite patients into our lab, but we're still having the patients do cognitive tasks. So in this case, it was a language study. So we still have the patients doing a language study that is very similar to how we would do a study on healthy control subjects. So there's no clinical recordings. We are doing, so you saw actually I think there's another bed here in the corner. Yeah, so there's, oops. So you see another bed here in the corner. So we have two beds actually, so we have two labs next to each other. So we are doing sleep research, but also for the sleep research, we're not studying sleep disturbances like sleep disorders. We are mainly studying the influence of sleep stages and dreaming on memory consolidation and learning. So again, that's like the cognitive research question, not so much the clinical research question. But then of course, if we're doing EEG during sleep, we are recording it according to clinical standards. So we are also recording like EMG on the chin, we're recording EOG, we're recording ECG along with it. So in that case, the EEG has way more detail than what we typically would record in a clinical setting, but we're not using it for clinical diagnostic purposes.
What's the function of the eye tracker?
Sorry.
What's the function of the eye tracker?
So the function of the eye tracker is twofold. First, it is to ensure that the participant is doing what we ask from the participant. If we tell the participant to look at a fixation cross, and then we're going to discuss this in more detail this afternoon with experimental design. But if we want the participant to look at a fixation cross, and we present the stimulus there, then we know that due to the retinotopic mapping, that the stimulus is going to appear here, because it's going to be crossed over the hemisphere. And that is something that we sometimes use, that we want to have a very specific cortical area stimulated. And then, for example, we can present stimuli at different eccentricities, or at different angles, or different eccentricities. Of course, that doesn't work if the participant starts looking at the stimulus, because then every stimulus would be foveal. So very often our experiments are designed such that the participant looks at the center of the screen. We have a fixation cross there, and then the stimuli are appearing somewhere here in the periphery, and not really far in the periphery, just slightly in the periphery. So that's a feature of many of the experimental tasks, is that the participant should not look at the stimulus, but should look at the fixation cross. So we use it for tracking what the participant is doing. Of course, sometimes we also have tasks in which the participant is actually instructed to move their eyes to a target. So sometimes we have a visual search task where the participant has to make movements. And then we want to track precisely where the participant is looking. In most studies, we don't use the eye tracker. So the eye tracker is not used by default, but it's used in quite a lot of studies, especially if you want to make sure that the participant is doing what we tell them to do. The eye tracker serves a little bit the same purpose as the cameras that we have. The cameras also serve to track the participant's behavior. If we're doing research with children, for example, or especially with very young children, then we cannot really expect them to follow our instructions. So that means that we're presenting very nice visual stimuli, and then the baby is sitting there and is looking away. Okay, if the baby is looking in that direction, whereas the stimulus is over there, of course, there might be an artifact due to the movement, but what is more important is the baby is not looking at the stimulus. So in that case, the trial in which the stimulus was presented has to be discarded from further analysis. So especially for the babies, we primarily use the video, and for the adult participants, we primarily use the eye tracker. Because the adult participants, they will largely do it correctly. The babies typically never, they don't listen, but they don't care, which makes sense. So that's the main reason for using the eye tracker. So these eye movements, they're relevant. And these eye movements are actually for some studies, eye movements are very difficult to prevent. So if you make very small eye movements, you get refreshing of the visual content on the retina. So you start seeing gamma band activity, both due to the eyes, but you can also see activity in the visual cortex, which are not due to the stimulus, but just by making these microsaccades. So that is the reason why we use these very detailed eye trackers, so that we can see very small movements. So sometimes we only care about the large movements, and sometimes we care about the small movements. You also had a question? No, good.
You showed the device for synchronization, right? And pretty much used to using live stream media for
What-
synchronization. So is there like a downside to using live stream media?
I will discuss that tomorrow. But you're right, lab streaming layer is an alternative to using hardware. We're going to discuss that tomorrow in way more detail. Yeah. So let me show the other lab, okay? So this is the lab that we primarily use for at the DCCN for adult recordings. This is the lab that we have at the Baby and Child Research Centre. Oops, not too fast, not too fast. This is a quick view. So this is at a different center. This lab is used primarily for EEG recordings on children and on infants. So that influences some of the choices in the lab. But basically, like some of the prerequisites, we need a sink to wash, like to clean the electrodes and stuff. We need towels to dry it. We have the same type of electrodes here. But here you can see something that is different. So this is an electrode cap with sponges. And I'm going to tell more about that tomorrow. But these electrode cap with sponges, we can apply them faster than the regular electrodes. And especially for young children, for infants, that is important because they have a very short attention span. And once they start crying, the EEG is not good anymore. So what we try to do is we try to keep the experiment as short as possible. So we just slap the cap on and then start the experiments. That does mean that the recordings might not always be of such a good quality, but at least the behavior is of good quality. And that, because that's always the challenge that we have, is we need to have a good quality signal, but also good behavior. Because usually the participants are doing something. They're looking at stimuli, they're doing a task. And if they're not doing the task, then we cannot use the data. So that's why in this lab, the time that it takes to prepare the subject is more relevant. So these are the active electrodes. They are sometimes still used, but now primarily these sponge-based electrodes are used. Each of them is like a very small sponge. And we have a bucket with salt water. I will show them a little bit later. Again, here you see two computers. One of them is the acquisition computer. The other one is the stimulus presentation computer. So those are the two computers. And here you see, so these are the buckets that we use. So that's where we soak the electrodes in. There's salt that we add to it. And you see the supplies, like the measuring tapes. And here's the distilled water that we were instructed to use for making sure that we have the right balance. Then over here you can see the actual EEG setup. So again, it's a separate booth. But now this booth does not have a Faraday cage. It still does have a door that closes as well. But here in the corridor, this is in a part of the building where there's not a lot of traffic. So this room is typically more quiet. Let me just, so here we're using webcams to track the participants' behavior. We use speakers to present sounds. And there's the bucket actually with an electric cap in it, like soaking until it is sufficiently wet. And here you see the amplifiers. So there's 4 amplifiers. So again, here we can do 128 channels, but typically we do 64. Sometimes we do the experiments with a maxi-cosi, with a car seat, if the baby is very small. Often they would sit on the lap. And since we want to keep the baby occupied, or the children occupied, there's toys that we play with to keep them distracted. Let's very quickly go back here. So this is what the So this is where the participant is sitting. And so at this moment, there's a study going on with, I think, 4 to 6 month old infants. So they're sitting on the lap of the parents. And a consequence is that they're sitting relatively low. So if you then look at how we've set the rest up, First of all, there's this white towel to block, to remove anything that is visually distracting, because they really like to look at stuff, and they will look at stuff that we don't want them to look at. So that's one of the tricks that we use. The second thing that you might notice is the angle of the screen. So the screen is angled downward, but that's because the baby is sitting on the lap. The baby is sitting much lower than yourself, and we want the baby to have a proper view on the screen. Something that we would do is, if the parents are in the room together with the baby, which is like usually the case because then the baby is more relaxed, is that we give the parents headphones and we present something different to the parents. So the parents don't know what the task is, because we don't want the parents to join in the task. Like if the baby is sitting on the lap, and if the parent, every time that the stimulus comes, the parent would do this, then of course we would get an artifact that is synchronized with the stimulus. Or we would get an artifact that's synchronized with one of the conditions. So that's why we keep the parent distracted, so that the parent doesn't participate in the task. Any questions about this setup?
Okay, question number one is the baby asleep or awake?
In our case, the babies are always awake. We're doing cognitive research. It's actually always task-related activity. So it's the baby is often. So this is like usually developmental research. So we're studying, for example, when the baby is capable of doing something that we know that adults can do. So we, for example, have tasks in how the baby listens to nursery rhymes, like nursery rhymes where the intonation would be more extreme. Like, and how do nursery rhymes help to develop language? So we would present stimulus material where we would have like language-related stimuli in a rather boring way of speaking, or in an extremely exciting way of speaking. So, and that would then be the experimental task, is like whether the two different ways of presenting auditory inputs to the babies changes the way that they learn. It's these type of tasks.
Okay, so at this point you're not recording the delta waves, it's just the...
No. Yeah.
Okay, my next question is baby allowed to eat during this process? Baby allowed to eat?
Eat? No. So
if the baby is crying or something, how do you calm down the baby? I'm looking at it's a little bit difficult to know what...
this is definitely difficult. So we try to invite the babies at a moment that is convenient for the babies. So we call the parents. And then we ask the parents, like, what is the regular sleeping behavior? And then we invite them during a time that they normally would not sleep. Because if they're sleepy, then they get fussy and they will start crying sooner. We also try to make the experience, both for the parent and for the baby, as smooth as possible. So if the parent is stressed, the baby will be more stressed. So one of the things that we also do is that if the parent has multiple children, and if the other children are not going to daycare, they can just come along, and then we take care of the babysit. So that the parent is relaxed, so that the parent does not have to stress about the other children going off. We have other labs as well, so and there's lots of toys in the other labs. So we just have a research assistant that would then take the other children into the other lab, play with them, while the experiment is going on with the baby. For the EEG recordings with children and with infants, a lot of the recordings are not successful. So we typically plan for many more participants than what we know that we'll eventually need for the analysis. And it is quite common, so it depends on the age. So the very young babies, they're easy. When they get a little bit older, they start moving a lot. When they get around 2, they don't want to wear electrode caps. When they're around 4, they're again easygoing. So it really depends on the specific age range, what type of problems we're going to get. Like the very young ones, we have the sleep and the fuzziness. The slightly older ones, we have that they don't want to wear something weird on their head. So that's something that our developmental psychology group has a lot of experience with. So they know how to distract the baby or to distract the child in order to make the experience as smooth as possible. And then we still have to throw away half of the data because of the measurements failing. So yeah, so that's how it is. But it's things such as making the electrode application procedure fast increases the success rate a little bit. If we can put on the electrode cap in 10 minutes rather than 15 minutes, then it means that we have 5 more minutes in which the baby is going to behave. And that's quite a lot, because quite often, especially with the young babies, recording is only 10 minutes. Like preparation is half an hour and recording is 10 minutes. Very inefficient, but that's just how it is. Yeah?
I need to understand these machines, how sensitive would be the effect of multiple power outages? Supposing you're working and the power goes off, when it comes back, you switch and everything goes on.
So to be honest, that's not an issue that we have in the Netherlands. No. So power in the Netherlands is extremely stable. So our computers are not on the UPS. The EEG amplifiers are on the battery, but that's not because the power is unstable, but that's because the power line that we get from the wall has 50 hertz. And what we want is the recordings not to be affected by the 50 hertz artifact. So that is the reason that we're using battery-operated EEG amplifiers. The way that the amplifier is connected to the computer is often through a fiber optic cable, so that there's no galvanic connection through which we introduce artifacts. So it's these tricks that we use. But if the power were to go off, which is very unlikely, then the computers would just basically fall out and then the recording would be lost. But it perhaps like once every 10 years. So we do have we also have like a large compute cluster in our building. We're doing a lot of analysis on the data. Our compute cluster is used for very long computations, also during the night, of course, because it's like very long computation. So our compute cluster has a UPS, so an uninterruptible power supply, because whenever there's maintenance done on the building, which is usually in the weekends or so there's no research going on, but then there will still be computations running, then the compute cluster would keep on computing. But in the labs we don't have the. So, actually in the previous video, so it's because I'm saying we don't have power outages. Let me check whether that's visible in the previous video. No, I don't think it's visible. So our building, no, it's not visible. This doesn't have it anymore. So our building is on the campus. The campus is shared between the university and the hospital. Our building was originally part of the hospital. So we do have 2 separate power networks in the building. And so some of the sockets still have a different color. So we have some sockets that are orange, and those are connected to the hospital's uninterruptible power supply. So that is for medical equipment. We're not using medical equipment, so we don't care so much. But of course, like for people in the hospital, it's really important that if there's a power outage, that the equipment keeps on working. So that is something that so it is visible in our building, but it's something that since we're only doing research nowadays, we don't really make use of that anymore. But yeah, sometimes if the power goes out at an unexpected moment during the week, which sometimes happens, then it's the orange sockets that are still powered because they're connected to the university or to the hospital grid. Any other questions? Yeah.
Thank you, sir. I want to know the function of the salt with the electrode salt solution. Is it
That's a good question. I suspect that we're paying for it as it's being special salt, but I think it's not very special actually. So it is a salt that is recommended by the manufacturer of the EEG caps. And tomorrow I'm going to explain more on how EEG systems work, and I'm going to tell more about the interface between the electrode and the scalp. So, but to be honest, I'm not really 100% sure whether it is just sodium chloride or whether there's, for example, potassium chloride or something more special. I suspect it's something very simple that they put in a jar and then sell it extra expensive to us. But we just want to make sure that we're not doing something that might break the electrodes, because these electrodes are very expensive. The salt is still not very expensive. Yeah, so the purpose of the salt water is that the salt is basically an extension of the scalp. So the skin, as Mikkel showed, so the head itself and all the tissues in the head are electrically conductive. And if we place an electrode on the scalp, then we're not always placing it directly on the scalp, but we're placing it close to the scalp. And then the gap between the scalp and the electrode needs to be bridged. With the salt water sponges, the sponge contains salt water, and the salt water acts as a bridge between the scalp and the electrode. I will show this in more detail tomorrow during the presentation.
I think it's also for sterilization. I think it's also that's
Just use the microphone so that others can hear as well. We share knowledge with it.
I think it's also for sterilization like that. That's the salt water. Yes, that's what I said. But to put the electrodes inside, or to use the salt water sometimes to clean the scalp and all that. So it's sort of addition to what he has said for sterilization.
Yeah.
I really think it's for conduction.
Oh,
And conduction.
Salt water
Yeah.
again is a very good conductor.
Yeah.
Again.
Yeah.
So it does a lot of things actually.
Yeah.
The salt water.
Yeah.
Thank you.
So indeed, sterilization is also an important thing. So we're not using salt for sterilization. We have a special bottle of, yes, it's called Secucept. I don't know what it is, but it's recommended as a disinfectant. And we soak the electrode caps after usage. We soak them in Secucept for 5 or 10 minutes, and then we wash that away. So that is our disinfectant procedure.
So the soaking is the soaking in salt
That's
solution.
it.
The soaking in salt solution is before the
Yes.
experimentation.
Yes, what I showed in the other video was indeed before the experimentation, and then after the experiment, we clean the cap, and then we soak them in the disinfectant.
Then one of the images and the video shows a part where you have brush. So if you are using that, I hope it won't.
Was it in this one?
No, I think the first video.
This is the first video. So here you see the bucket in which we soak the electrodes afterwards.
So you just soak and bring it up. That's all.
We brush it. We brush it with a tool. Actually, so that is something that you can practice tomorrow, because tomorrow we're going to do EEG experiments, and afterwards we need to clean. And I hope that you're going to do the cleaning, not me. So we use a combination of like brushes, depending a little bit on the cap. So I brought toothbrushes with me and small dental brushes, like dental for cleaning between the teeth. It depends a little bit on the shape of the electrodes, which brush is convenient. Where we typically first rinse the cap, and then go over each electrode with a brush, and then we would rinse it again, and then we would disinfect it. That is the standard procedure. I did not bring disinfectant here, so tomorrow we cannot disinfect, but I'll do that like next week. Any further questions about this?
I have a question. Just a comment, sir. Thank you very much, sir, for your presentation. Actually, when you talked about the EEG system and the cost, giving us a range for about 1,000 to 30,000 euro, then for the computers, acquisition, and stimulus production for about 1,500 to 3,000 euro. I was a bit happy, like it's affordable. But along the line, you told us that the amplifier is separate, the cost separate and the electrodes are separate as well. So I got like, wow, broke my heart.
So the so this is also where it might be different. So we already have the labs. So whenever we buy something new, we always buy it as an individual component. We have a long contract, like a long-standing collaboration with Brain Products. They have a Dutch distributor, and we're not negotiating on everything that we're buying from Brain Products. If somewhere else at the university, if a new lab is made, which occasionally happens, then you negotiate. And then you're going to negotiate a price for the whole lab. So you're going to say, I need this and this and this and this, and how much discount can I get? So that is something that in the maintenance of our labs, we don't do. Because we're not in a situation anymore. But when we initially bought the first amplifiers, we negotiated and we got the price down. Because these companies, they have a lot of margin on the prices. If you let me just get one of the small amplifiers, okay? Let's see where it is. So this is one of the small amplifiers that I bought. This is an 8-channel amplifier. It's about €1,000 if you buy it, and then you get electrodes with it. I've opened it. I've looked what's inside. I've looked up the chips. The component cost is not really more than 50 or 60 euros. So if you subtract all the electrodes, you could say, well, the amplifiers perhaps would cost me 500 or 600 euros. But the components are only 60 euros. So the company is making like a 10-fold increase. But that's because the company put a lot of work in it. And that's usually where we negotiate. So we know that the company is not selling the product because it's expensive to make the product, but it's expensive to design the product. And that's where these companies put a lot of money in. A lot of our former students are also working at these companies. So I know that, and these students, these employees at these companies also need to have a normal living. So their salaries need to be paid. So that's why I know that making such a thing, even though if you would solder it yourself, it would only cost you 60 euros. The time that it would take you to design it, it would take you months, or perhaps years. And that's largely what we're paying for. But it also makes the financial model that the companies have rather complex, because companies actually, if they would sell such an amplifier to you for 100 euros, the company would not make a loss. But the company would also not make profits that they need in order to pay their personnel. So that's usually why there's a very large margin in which you can negotiate. And then of course it depends on how important you're considered as a customer and how willing the company is and what you have to pay. One of the other amplifiers that I have, we bought it for half the price. For half the price that was listed. So we first got a quote. It said, 16,000 euros. And then we said, can we get a discount? Oh, you can get it for 8,000. So it was a significant price reduction by us explaining what we needed to amplify for, and that they were happy to have us as the customer. But that's buying multiple things together often gives you more room for negotiation.
Also, I was wondering whether your interaction with them one-on-one, you know them, met them, might also change the dynamics, might help to reduce the price also. I know when I was at SFM sometimes I met the company and we started talking. A lot of our interaction was to order something. They do certain things for me. Yeah. So sometimes when we go for conferences, we meet these suppliers. I think sometimes I also go very
Yeah. No, it's indeed like knowing the companies helped a lot. And since I'm working in more on the method sides of neuroscience, I know a lot of students that end up in these companies, and then I have my contacts in these companies. But still, the salespeople in the companies are not necessarily the people that I know. I know the technical people, and the technical people don't have the leverage. So for the companies, it's really important. At least for what I know, for the companies, it's really important to set up like a long-term financial agreement. Like it's not really an agreement, but if a company gives us a discount, it's because they expect that they can make money from us in the future. And that's what we understand. And of course, we're not giving them a guarantee that we're going to buy from them in the future, but if we're happy, we will. And then so it means that on the first sale, the company might be losing money, and we might be lucky, and later we are losing money. Oh, yeah.
Well, there's always something that troubles me. I think most of this equipment came from the laboratory, and then they go to the company, and they make them, and they sell. Are we no longer in active practice of trying to come up with new equipment or even make these? I was in San Diego and I went to a lab and I saw stereostatic apparatus and the base were being made from a pharmacology lab and still sold in the US, and money was being made from the university. And I think if we are also ingenious, rather than depending on this company, you might start thinking about how
Yes.
to make out.
Yes, I think that is an important realization. Like you can make this yourself. Tomorrow I'm also going to show some of the equipment where I've been doing some stuff myself, and we can discuss this in more detail. It's like, so what do you do yourself, and what do you rely on also for commercial support today? Because it's not only about buying, but it's also like supporting it, and supporting also means answering questions. And that's like one of the things that I would find very difficult if I were working in a company, is that you have to ask money if you sell the product, and then years later you still get questions about the product, and you still have to answer those questions, and then you're not getting money for answering those questions. So and of course which means that is something that you have to put into the initial price. It's different than if you buy a car. Like if you buy a car, you know that you're paying for the maintenance. But you're not really you don't really need support for a car. Whereas for EEG systems, there is often support needed. So I know that is something that the companies are actually spending quite some money on support, and they're not making money with support, but they're making money with the hardware. But there's so EEG labs can really vary a lot in range from low cost to high cost, and it depends a lot on how much you can invest yourself, not only in money, but also in expertise. Because the more expertise you have, the more freedom you have to choose from the available equipment. Let me get back to my slides. So tomorrow I'm going to tell more about EEG hardware, how it works, and we're going to tell more about how EEG is integrated in the lab. So we can discuss more on how to, like what are the choices that you have, especially if you work together with people that have more of an engineering or a physics background, and how that can help you to set up the lab. I don't want to focus a little bit more towards the scientific side of things. Like as I've told you how we've organized the labs. But I would say that although at the DCCN we have very fancy labs and very good support, then it's not very typical. We are only doing cognitive research. So questions like where's the visual stimulator, are the babies sleeping? No, all our participants are awake and are doing a task. A lot of our research is done with MRI scanners, with functional MRI scanners. So actually a lot of our research paradigms are designed to be done by someone who's lying on their back looking at a screen. That's a very unnatural posture to be doing a task. So also in EEG, the typical task is with the participant sitting still. And as such, we're missing opportunities Also, most of our tasks are done with healthy young participants. Our typical participant is a university student. Like not always, sometimes we have patients, sometimes we have elderly participants, but most of the time it's with young, healthy students, which also makes it weird. Like, because the students are typically rich, well-educated, etc. So as such, there's a lot of bias. We have, since we're doing this at a large scale, we have very well-controlled, soundproof, and distraction-free labs. For example, for this language research. So the founding director was a language researcher, so he put a lot of effort in that. But I would also say that something that makes the DCCN unusual is that we have multiple neuroimaging methods, and they're all available to all the researchers. So that means that the researcher will use the method that is most appropriate for answering the research question. So if we want to know where in the brain certain type of activity is happening, we're most likely to use the fMRI scanner. Whereas if we're interested in when it's happening, we would use MEG or EEG. So we have this flexibility, and that's of course a flexibility that most labs don't have, because you don't have all of the equipment. The consequence actually also is that nowadays the EEG is not used that much anymore. So we're using more the scanners than the EEG equipment. So what I just want to say here is that like the DCCN does not explore or utilize everything that EEG has to offer. So as such, I would also say our labs should not be the example for your labs. There might be some things that you might want to copy, but there's also things that I know that other labs have much better than our labs. For example, with EEG with participants that move around, or EEG in the field, like as we're doing the recordings here, but that you take the EEG system towards the participant rather than the participant coming towards the lab, which is especially important if you want to do EEG on large cohorts. So at a certain moment, we did have a EEG system in a van, and then the van would drive to school, and then the kids would come out of the class to participate in EEG research, and they did not have to come all the way to the center. I think those are really important ideas as well, because you cannot put an MRI scanner in a van. But an EEG system in a van is actually not that difficult. And the advantage is that it's automatically you have the Faraday cage, because you basically have this large metal box. So EEG in a car is definitely possible, or just mobile EEG as we brought it here. And we're going to see tomorrow how successful that's going to be. Totally switch topics. So this is about like EEG in Europe versus EEG in Africa. African hair is very different than European hair. And that's something to be very aware of. So we have like this type of hair, a little bit, you can't see it anymore. I had a little bit curly hair when it was still longer, when I still had more of it. Most of you have this type of hair. So that basically means that it's very curly, and you also have a lot of hair. I don't have a lot of hair anymore. So for me, applying EEG is very easy. For you, applying EEG, like for example, if I look at your hair, I think that's going to be challenging. So I know that there have been groups that have specifically looked at the development of EEG electrodes that are better compatible with African hairstyles. And those are mainly groups, research groups in the US, because there are so many African American people that in the US, this is really something that they have to think about. In the Netherlands, we don't have that many people of African heritage, so it's not something that we typically encounter too often. So that's also why I don't have a lot of experience with it. I only did once a recording on a participant with a very large curly African hairstyle, and that still worked fine. But especially with the braids and the hair pieces, etc., I think that is challenging. That's also something that I would like to explore a little bit more tomorrow, when we are basically doing this like in smaller groups, that we have a little bit more of a discussion on this. Also tomorrow I'm going to talk about the different type of electrodes that we use. One of these electrodes that we use are like these cup electrodes, and this is a system that is developed for actually placing these cup electrodes, these clinically used cup electrodes, in between braids that are specifically made. So this is like really like an interesting strategy, is that the participant comes with the hair braided in a particular style, so that the electrodes can be clipped in between the braids. To be honest, I don't know how practical this is. This is a relatively recent development. Tomorrow, when I'm going to talk about the EEG electrodes, different types of electrodes, I will come back to this, and I will discuss why I think that this might not be the most practical for all cases, why gel electrodes are probably better. But we're going to discuss this in more detail tomorrow. Another thing that is like quite different between Europe and Africa is hair preparation. So the electrode contact is the best if the hair is clean and if it doesn't have any products in it. And the hair should also be dry. That's also important. In the Netherlands, most people have straight hair and don't really use a lot of products, except for some specific age groups. Adolescent boys, like teenagers, they often use like wet look gel. And elderly ladies that have like thinning hair, they would often use hairspray. So what we do is we tell our research participants that they should come to the lab. So we send them an EEG information brochure prior to coming to the lab. And in that brochure, it gives instructions to come to wash your hair the day before and not to use any products. So to be honest, I don't know how that works with you ladies. But I think this is really one of the things that you have to consider, because I think that in the Netherlands, the hairstyle of the women is more compatible with using EEG than the hairstyle here in Africa is with the women. So the male participants that I see for tomorrow, it's like the EEG participant, those are going to be easygoing. Like you have a lot of guys here with short hair. That's going to be relatively easy. Being totally bald is not necessarily good for EEG, because if your skin is exposed to the sun, the skin layer gets thicker and drier. So bald people are typically more difficult to get good quality EEG from than from people with a decent hair covering. So that just like some things to know about like hairstyles. So this is something that I would like us to discuss in more detail tomorrow when we do the practical and once I've explained the different types of electrodes. So for the female participants, if you want to be a participant tomorrow for the EEG, like if you want to wear the EEG cap, this is something that you can think about. So like if tomorrow morning, if you just, I don't know, but I can also imagine that there's certain hairstyles are basically not something that you're gonna redo in one day. But it's just like a consideration, okay?
Here in Nigeria, what you do is that you tell like how Nigeria is qualified to be our subject model. So you just make braids, what you call all back.
Uh-huh.
Or what do they call it? Oh, hair, cornrows.
Cornrows.
So you can make it like 10 or 15 all like to the back, and then she'll be able to wear the cap. But no strings, no all this, because if you do this, you'll not be able to place
Yeah.
it. Thank you.
Okay, so there are certain there are certain practical differences. There's also another dimension where Europe it has its peculiarities that I happen to know about, where I'm not really sure about how things are here in Africa or in Nigeria, and that has to do with the ethical and legal differences. Later this week, we're going to have a full lecture on this. We're going to like explore this in more detail. But the Radboud University, so where I'm working, is part of the Netherlands, which is part of the European Union. Copenhagen University, where Mikkel is working, is in Denmark, which is also part of the European Union. And the European Union basically dictates certain laws. So certain laws apply on the EU level. And some laws are made at the country level. So whenever we're discussing ethics and legal issues, it's always a little bit unclear because largely they're the same for Mikkel and for me, but they're not always exactly the same. And especially some EU laws are interpreted differently in the different countries. It is important, so that's what we're going to cover later this week, probably on Thursday, is that there's regulations at the regional level, at the university level, and at the departmental level. In Europe, the important regulation that applies is the GDPR, the General Data Protection Regulation. And that applies to all EU countries since 2014, and it's implemented slightly differently in the different countries because of the different interpretations. It is also interpreted differently by different universities. So in the Netherlands, some universities are more strict, whereas others are more liberal in its interpretation. And in the USA, there's something similar. It's called the HIPAA, the Health Information Protection Act. So it is important to know about these differences, and this is where I know how it is in Europe. I know a little bit how it is in the USA, but I don't know how it is in Africa. So that's what Damien is later this week is going to provide more input on. So I did have a little bit of like how the situation is in the Netherlands, because that actually affects, that has consequences for the procedures that we follow. So in the Netherlands, we have a law on medical scientific research on humans, and that specifies under which conditions that research can be done. And the requirement that we have, which then affects the way that we organize ourselves, is that a plan needs to be made in advance and it needs to be evaluated. And depending on where you're working, the evaluation happens either at the central level or at the regional level or at the local level. So for the DCCN, we're evaluated at this level. For the social science faculty, they're evaluated at this level. And then we get an approval, and these approvals are, for example, published. And I think this is something that might be actually quite interesting for you, because the open style of publishing what the research plans are means that you can look at how other people have requested their research plans. So that's also why I put these links in, because you can get quite detailed a priori plans of how research is being scheduled in advance, which of course you can use for planning your own research. But so later this week we're going to talk more about the ethics, etc. But it's more like how does this translate into the practical situation, is like with informed consent and all those type of things. So that's what I had as like differences between EEG in Europe and Africa. So are there any questions or comments on this?